Do all your shopping before the weekend because everything will be closed.
Really?
Yeah.
But that didn't happen.
Not that good. Maybe say something else.
In the first quarantine, that didn't happen. I read that shopping malls are going to be closed.
Yeah.
But at least you don't buy things at your shopping mall. It's okay. I think supermarkets are going to be open.
Yeah. Okay. So we have a new.
Yes, and I have them updated now.
A new version of notes.
It was 2-3 days ago.
Yeah, 2 or 3. The one we spoke about.
Yeah,
It's still there.
my friend is the master.
Yeah, it's that. It's the same one.
I think printing them is probably
I
not
know it is so.
the most ecological option.
I'm going to buy a tablet.
I mean, I really like to have the printed versions, but okay.
Yeah.
But if they are changing all the time.
We've also been given exercises in the new version.
Hmm?
Exercises on the first part of the course.
There's a whole section at the end. I didn't get to see them all. The first one seemed like easier than the ones that
They are
really.
Yes. Okay. No proofs. Thank God.
But then at the end there were exercises about random walks, which
Yeah.
a couple of them I will pick them from that section. In fact, I think Matthew is probably going to analyze more the exercises that are in the text because like they are part of the theory. So he's probably more motivated to doing that. So we should probably focus more on the exercises at the end, which
I have
are more disconnected in a sense.
I have a request. So I understood that I was having trouble with generating functions because there was a lot of jargon, a lot of terms from set theory that were being used. For example, I didn't know what a recursion was.
Recursion?
Yeah, I didn't because I haven't said I didn't know
Okay.
that.
So we'll start recording, I'm sorry, because it...
Okay.
Can you state again the question?
Yes. So sometimes very mathematical concepts from courses that at least I have not studied comes into the text, and that's where I get confused. So is it possible for us to compile a list of prior knowledge, like April knowledge that we need, so that I can do that? Because when I went to the library and I got books from set theory, I read those. I did
and it was much more clear. But I think it's easier if you ask the questions and then I respond with a little note, like I don't know what this concept is, and this, and this, and this, and then I write and I say, this is this, and this is that. Because if not, I don't know how far to go. That's you have to measure in a sense.
Thank you.
But that you can do it online.
On Slack.
Yes, because you're not asking a lot of online. Probably now that we're going back to more online version, we should probably use that resource a little bit more.
Yeah.
Okay, for today there were 2 chapters, one which was more on balls and boxes, something like that, and the other one that was on random walks. I don't know how much were you able to read, study, how much did you get? So, in a sense, the first of these 2 chapters for me, it was more like a complete application to a more or less complex problem in which you got to use a lot of stuff. Like it was not one specific subject, like random walks, it's one specific general set of tools and problems. The chapter on more balls and boxes, it was more like, okay, you have this problem, now you know combinatorics, you know generating functions, you know random variables. Let's put all this together into trying to tackle different questions in this context. I don't know if you got the same impression. Did you all get to read that chapter?
Yes, and this was easier because we've done random work in another course. So we're doing it simultaneously, we're doing it in another.
In which course?
Biophysics.
In biophysics. It has some kind of biological meaning.
Microprocessors. So it's actually pretty good.
The random walk, not the boxes and balls.
No, just the random.
The random walk makes sense, yes, because then with a random walk you define the winner process, which is like this thermal drift in a sense. Okay. And in this chapter of balls and boxes, there weren't many exercises.
No,
I get the feeling that the most difficult one was to prove the proof of the Poissonization trick.
Yes.
Perhaps we can discuss that.
Yes.
Before that, there was an exercise in which you had to prove recursion. I don't know, but I think it was easy. Did you think about it? Did you get it?
Which notes? Because
yes, I have the old. This part I already did with the old version. In the new version, it's footnote number 96.
96. Okay. I think we did it in South. That's what we tried.
You did with Matea?
We weren't able to do it.
But you got the idea of it is like putting in the first in n plus 1.
But that's we couldn't prove it.
But I think there is no much computations. It's just realizing the meaning of the equation. So the idea, just to comment a little bit, it would be from now on I will use footnotes and X for exercises. So because now we have two different flavors of exercises. This would be footnote 96 for now. Who knows what it will be in a while. And the idea was first to prove a recursion, which was this guy is. Sorry. Do you want to change?
Yeah.
So the meaning of this it was the number of ways of distributing R balls in n1 places so that all of the boxes have at least one ball. And the idea was to prove this recursion. So in this sense, you can reduce the n plus 1 problem into the n problem. That is why it's a recursion. And what is the meaning of this? Did you get to discuss that? Can somebody explain it? So you have all the boxes. And if you have to say this with words, not talking about the equation, what is this equation saying? Okay, essentially you're adding this place.
For R balls in n plus 1.
So essentially it relates the problem with n boxes, which is this, with the problem with one extra box. And it says, so the idea is, how can you manage to have all the boxes occupied in an n plus 1 problem, talking about an n problem? Okay, it is easy. I have an extra box, so the thing I have to do is to ensure that this extra box has at least one ball. So it can have 1, or it can have 2, or it can have k balls. And then I am left to distribute, if I put k balls here, r minus k balls in the other boxes. So it is essentially the combinatory expression that states this. Having the problem with one extra box is equal to assigning whatever possible number of balls to the extra box, and then making sure that the other ones with r minus k balls are all filled. Of course, then the relation was written like this. But of course, a lot of these terms are going to be 0, right? Because if you put, for example, all the balls in here, then it is impossible to fill all the balls in here. You have at least to have n balls left. So in reality, what is the maximum value you can put in here and still be able to fulfill the condition on the other boxes?
R minus k plus k equal n. R minus k equal n.
This has to be larger or equal to n. So k has to be larger than r minus n. So really, you can reduce the upper limit into this. And then this coefficient is just saying, okay, you say that here you're considering the situation in which you are putting k balls into the extra box, but there are many ways in which you can choose those balls. So this is the meaning of the combinatory. So then perhaps you can try to put it.
We kept on trying to change the variable. That's why we didn't option. Yeah,
Because we tried to prove the second as well last week.
You try to prove?
The second one.
Show that the generating function. There's a second question.
Show that the generating function is given by. But I think that part was just putting the expression. Okay, I thought about it without using this. I'm just saying, if we have the probability, then we have also A, right?
Oh, because we went back trying to use
Yeah, we use this to try to show.
Okay, so the only thing I did was saying that if you had the probability of not leaving any box, without balls, then you can write A Rn as the probability of this happening times the number of ways of assigning balls, which is essentially the first ball has n options, the second ball has n options, the third ball has n options, so n to the r. And then I use this relationship.
Now it's easy. Yes.
It's easier you see the answer.
We were expecting this.
But I think it was more interesting now it's the second exercise in this footnote because another one was added. the exercise in footnote 99, which was to prove the trick of Poissonization. Do you remember the general idea of Poissonization that was discussed in the text? It was like you have, it is essentially the situation you have in here. You have that you have a random sum that is bounded to some number. And the problem is that all these random variables are not independent. You see the number of balls in each place as a random variable. Why? Because the balls sum to R. So, for example, if all the balls are in the first place, you for sure know that the last place will have 0 balls. So no independence here. So the trick of Poissonization is to write something of this style and now replacing the value of the sum by a random variable, where the random variable now is a Poisson with some mean. And the magic is that now the values of all the terms in the sum, they are independent. And they are again Poisson. So the thing is, how do you prove this? That's the idea of the exercise. The meaning of this approximation, when is this going to be useful? When this number is very large. Because in that case, then this random variable will be very close to the mean. So replacing this by a Poisson random variable that has that mean equal to this deterministic number will be very close to having the original sum. When this value is 5, this is not going to be close. But when this is 5 million, okay, then the random variable, this random variable with mean 5 million is going to be more or less a good approximation. Okay, in the exercise, this was the objective, but I propose an easier exercise. So the case in which you have 2 values. And do you see why this is enough? Because you can do like an induction. If you think you're adding an extra box, you can think this random variable is all the previous boxes, and this is the new box. So proving it for 2 boxes is enough, and makes all the computations much nicer. So do you want now to think a little bit this? I will break apart the exercise into first one objective. What is what you're trying to prove? Because now it is in words. In words, we are trying to prove that if this is Poisson, then this thing is also going to have that distribution, and again with different means, and they are going to be independent. So first objective, not to try to prove anything, but to know what you're trying to prove. So take a minute to read the exercise and try to transform the exercise into a set of equations you're trying to prove.
there are just two X's, right?
Hmm?
If we have only two X's, then it's the same equation, but it's basically and will go from 1 to 6.
It's the same equation. Do you want to write it? No. You want to tell it to me so I write it?
It's this. But should it be n or should it be 2?
That is literally the distribution for a generic sum that is equal to one deterministic value.
Yeah.
But you're saying something more. You're saying that this takes a special form,
Okay.
right? Which is not that generic form, it's a specific one.
Is it the Poisson distribution? So I wrote down the mean there.
I'm going to add one thing. So try to think, what do you want to prove and what do you know at the beginning?
So we know that that R follows the Poisson distribution. So we write that down.
You know this? Yes.
And then we want to prove that X and X1 and X2 independently also follow the Poisson distribution.
Yes. And what do you know about them?
That they're independent.
No, that's you want to prove. But you know that given a value here, these two values are the number of balls that fall if you put randomly balls. So what is the meaning? This is a random value, but when it takes a fixed value, then x1 and x2 are these values that are constructed by putting balls randomly in each one of the two boxes. So they are like trials in a sense, right?
we have two boxes in this case, and we have x1 and x2, then how many balls can we, how many ways can we put balls in those two boxes? Is that it?
That's a way of thinking about it. Another way is that I like perhaps a little bit more is that I think that I do this sequentially. I take one ball and I randomly say left or right, and I put in one. Another ball and say left or right. And that, if you think about it, constructs a random variable that you know.
Yes, yes. So we write that equation.
That is the thing you know about the x's, that they have this distribution. Given a fixed value of this, not in general.
I feel lost because I don't know what are you doing. This is 99 from what page? I don't know.
I don't know if you have the.
Yeah, but I have the last notes.
Do you have the last notes?
Yeah, but I think that is that because they say personalization. Yeah, it's the same.
But the second exercise.
It's
Yes.
oh, okay, because
I was saying like don't do it for
No, page
the
okay, but we have to
variables.
do this. No, I would read it because
I know if the exercise changed. I did it when it was in the other notes.
oh,
Let me check. Which page is it?
page 81. Can you please
Sure, you can have this.
look to see if the same exercise? Yeah, it's the same.
It's just different notes. Are you guys shifting to?
No, no, Hudson, nothing.
Yeah,
Maybe tomorrow, Friday.
I don't know.
I want to go there
Yeah,
because I feel that
still.
so close to us. I have to yesterday
Yeah.
because I was
R is
for
Postgraduate,
and
that's why the next two
you are
I'm sorry. You want to prove that if I need Poisson?
but I feel
The
that
X summary should also be worse here
because there are too much information.
They also have that distribution, but with a special mean that is on the exercise, right?
Yeah, I want to write to
But you want to prove that. But when you have two random variables together, is it enough to know the distributions separately?
Oh, do we have to find the generating function? Because if we find that, no.
Perhaps you can do it with generating functions. I don't
We
know. I
can
did
do
it
it
another
like
way.
that.
Do?
We can do that as well.
I don't know. I didn't think it in that way. Perhaps if you want to try, then we see it. But I did it directly with. I did it directly with properties of probability, nothing more. Just writing down what you're trying to see and.
I have an equation, but I'm not sure. I have to, I'm not sure.
You want to write it?
I'm not gonna do it. Yeah. So I just base it from the equation 110.
What?
Yeah, from the equation 110.
110.
That's what I did before. Yes.
Okay.
Oh, I don't have that anymore.
I don't have that anymore.
Maybe I can send a message in the Slack right now. There's no equation on it.
What I thought is if we want to show that probability of x1 and x2 given r is equal to just the product of the probabilities.
It's just seeking. Because this exercise was not in there when I thought about the exercise. That's why you are now trying to use it, and it's perhaps a good idea. So you're saying you have equation 110, I read it, that says that the probability of having the first value equal to x1 and the second one equal to 1x and the n1 equal to xn, given some value of the random variable r, is equal to some normalization constant, the probability, the product of the individual probabilities of these values, which would be times the delta, which says that the sum would be equal to r. And the previous exercise says that if you choose a random variable that has distribution equal to AR, which is the normalization constant, then you win, in the sense that you make everything independent.
It's not one of it, yeah.
Yes, it's the same. I mean, you can look at it as
I wrote it the other way.
Yes, because QR is.
Okay.
Yeah, because I, yeah.
Just to keep the notation.
No, but this is what I said initially, and you said that we have to write the first.
No, that's, you know more than that.
Yeah. So,
Because you wrote it for generic random variables, but they are telling you they are multinomial.
So, so would it just be lambda, like, I don't know, P1?
If you try to follow this using the previous exercise, you would have to compute AR for this,
Yeah.
and then prove that the AR that is correct gives you the random variable R.
Okay. But that's not what you're asking us to do.
No, but then this trick, I think it doesn't work. Because here the random variables are multinomial, and when you choose like this, then you get that the joint distribution is factorized and everyone has multinomial distribution. But what you're trying to prove is that when you choose Poisson here, then these are Poisson, they don't have the multinomial.
Yeah.
Which is a different conclusion than using this.
So you mean what we want to prove is that if R is 1,
Then these two are independent and they are Poisson.
R independent.
If you choose the Q in this way, you don't get that they are Poisson. You get that they are still multinomial.
So do we write down the distribution of R as just the Poisson distribution, which is lambda count P exponential minus lambda over P, factorial? What do we write? I don't understand.
So you're saying you have the distribution of R, which is the distribution of the
lambda.
right?
Yes. Yes.
Okay, this is the third thing you know. The second thing you know is the distribution of these variables independently, which is the same, and in the case of two, a multinomial is just a binomial. So you know that the probability of x1 equal some number k given r is equal to binomial. This is, we have r trials, k successes, b1 to the k 1 minus P1 divided minus K. And the probability of X2 is the same as in failures.
Yeah, it is either X1 or X2.
So you know all this. And what do you want to prove? So this is a conditional probability. It's not the real distribution of the random variables. In fact, what you want to prove is that the unconditioned probability is not the same. It is in fact a Poisson. So we want to prove that Px1 equal K is equal to e to the minus lambda P1 lambda P1 to K over K factorial, which is to say it's just a Poisson with this mean, and the same for the other one. But with the correct mean. Is this all you want to prove? And you also want independence, because knowing the two distributions separately doesn't tell you anything about how they look together. Together they may have interactions, correlations, and the distribution may be different. But the other thing you want to prove is that so this is what you know, this is what you want to prove. And perhaps doing the computations will take a while, and it's better to move on to random walks, but what do you need to do for this? So you have to prove these equations, essentially, 3 equations. These 2 are the same. If you prove one, the other one is completely analogous. You have to do that. You have to uncondition this relation, which is what she said. It is using total probability for the random variable R, essentially. So what she said is multiplying this by this and then summing over R, which is the same as unconditioning the random variable. Why do you want to uncondition? Because you know a condition probability and you want to obtain an unconditioned probability, which is the general strategy you will try to use. And then you want to also prove this, which is a little bit of algebra. It's nothing more than that. Essentially, the trick is the same. You want to obtain this through conditioning using total probability and then reducing it to what you already know. But general idea, I am a little bit insistent in this. Know what you want to prove before trying to prove it. because if not, it is a mess. So you have an exercise that is a little bit confusing. I mean, it was not easy right away to know what you had to do, but so transform it into the things you really want to compute, and then write exactly what you know through the text on the exercise. And then after that, say, okay, I want to connect what I know to the things I want to prove. And then you develop a strategy. And the strategy was easy once you knew the things you knew and the things you wanted to prove. But previous to that, it was, you know, at least confusing. And the rest of the chapter, it used a couple of times the generating function of the Poisson to use these tricks of Poissonization and stuff, but the computations were more or less easy, I think, and there is not a lot to do also. So perhaps it's better to go to the exercise at the end of the notes on random walks.
Which one?
110.
110? Without 110 or 113?
The page, you mean?
Page is not, I guess you can.
And the exercises begin at
Oh,
110, I think.
The exercise.
Yes.
Like, the ending. Got it.
The exercise I recognized as clearly talking about random walks were the 20, 21, 23, 24, and 26.
We don't have the exercise in our note.
Yes, we do.
It's in the.
It's at the end of the notes,
Yeah.
not in the text. Like
Yeah.
you have a note version.
Yes,
Yeah.
I think it is.
So 110, page 110.
Do you think that there are the exercise that go
No,
to
you have a note version. Sure.
Exercises.
Exercises
On the first part.
This is the first part. Yes.
Sure.
Because the professor said something about the exercise about the go for the exam.
That's these.
Okay.
I know it's a mess because versions are changing all the time.
Yeah, it's
It's difficult to keep up. Happened to me last time.
Honestly, I'm killing so many trees because of these notes. I feel bad.
Hmm?
I'm killing so many trees. I feel bad.
But this is what happens when the nodes are developing at the moment. I mean, it's a little bit inevitable. Okay. Have you taken a look at the exercises or
No.
not at all? Then perhaps we choose one at random and discuss it a little bit.
But
because-
for
which?
random walks. Yes.
Random walks, yes.
Yeah.
Perhaps you can tell me what was a little bit difficult for you in the chapter or something like that to choose one appropriately.
I didn't understand very well when they talk about the part of the reflection principle. There is a part that I didn't understand because I think that they say the same. And I don't know if there are an exercise
Let me see. I don't remember.
would be
It's
similar.
this.
Yeah,
87 in the beginning.
87. Yeah, the exercise that they show, I think that
Do you find it?
I don't think I see an exercise that
There
is so.
isn't an exercise for this.
no, I didn't see any exercise. No.
I don't think I see an exercise in which you use reflection principle. Okay, perhaps we can discuss it a little bit. What was confusing for you?
No, it's I don't know. I think that I don't understand because I talk about the previous exercise about the elections and they included here, but this part I didn't understand. And this.
Do you get the general idea of the reflection
Yeah,
principle?
I have the idea, but this part.
So you don't know how to go from
No,
this
it
expression
was
to the other one?
confused. Yes.
Because now he's just using the
Yeah, but
reflection principle
yes. But
for this equation. Then he uses
there
magic
are a lot
algebra
of
to go to,
combinatorials and
but that's identities from the
Yeah.
coefficients. It's not, I mean, you should write the definition of the coefficients and try to play.
yeah, because
For myself, I didn't do it. I was like, okay, I believe you, Mateo.
okay.
But I mean, in there, the probability stopped.
Okay.
Now it is just writing the definition and see how you manage to
Yeah.
group them together. And
Okay.
There will be one difference. It's the coordinate difference. It's a difference of coordinates.
different. Okay, the first one is easy, the 20. Perhaps start from that. It is the one with the matching boxes. I will tell you how it is. I will give you the.
I have it.
You already have it? Perfect.
This one that has to go.
Exercise 20.
Page 110.
Just a couple of words before starting. What is the magic of the reflection principle? Is that there is something you don't know how to count, which is the ways of reaching one place without touching the bottom. And you reduce it to something you know how to count, which is directly the ways of going from one to another place. So a general idea in this random walks is to try to draw things and recognize the paths you're trying to see, to reduce it to saying this is the probability of a random walk going to one place from one place to another place. Once you reach that, then you end because you already know the answer. It's in the chapter, it's the number of ways of going from one place to another one. That's it. Okay? So in this exercise, the idea is the same. You have to try to write the probability that they are telling you to compute. Try to write it like something like a random walk at some number of steps is equal to some value. So essentially what you have to do is to give values to m and k. Okay. Once you do that, then you know how that probability behaves.
Can we assume that in part 1, both of the boxes have N matches.
Have?
N matches.
Isn't it on the...
Sorry, R matches. Okay, so, no, N matches. Both
N matches,
have
yes.
N matches.
Yes.
So if it's the last match,
So you want to compute the probability
Is
of
there a site?
one of the boxes is empty, the other box has, I don't know,
R matches.
R matches?
Yes.
R matches. So the probability of arriving into this situation. And for this, try to translate it into probabilities of some point in the random walk. And the probability of choosing one matchbox or the other one, it's always 1/2.
Would K be 0 this entry? If one of the boxes that is K equals 0 because there are no boxes, there are no matches left.
Depending on how you're describing the random walk. But if you're describing the random walk in terms of only one box, then that random walk doesn't have information about the other one. So it's probably not going to be a good idea.
Which wouldn't be random walk in this case be, the smoker doesn't know which box he's picking out. It's random, right?
It's random, yes.
So there's one possibility he picks a match.
He picks this one with probability 1/2 and this one with probability 1/2. That is the same.
That's it. But he doesn't know. I'm trying to visualize it, but I can't see it.
I mean, the model is picked so that it matches a random walk. In fact, in the second part, they say, okay, now imagine that the dynamic is different and it's not a random walk. So the idea is, each time he has a cigarette, he chooses one pocket and he uses one of the two. You have to encode the information of both in one random walk. Because I don't know, but perhaps you were saying with probability 1/2, this box loses one. It was like a random walk that was always going down.
Yeah.
With some probability it stayed and with some probability it went down. That is no good because you don't know if you have this number on the other one.
probability is 1/2, will it be like a Bernoulli trial?
Okay.
Like a Bernoulli trial? If the probability is 1/2.
When you see at a given time, it will be like Bernoulli trials.
Okay, so if one of the boxes is empty, then that has 0 matches left, and the other one has R matches left, which is n minus R, and this n is 1. So if both of them had 2n initially, it is 2n minus n minus R. That's it. I'm trying to.
Okay.
Yeah.
So essentially, you're trying to see
Yes.
these two things. The first one is how many steps you took.
Yes.
Which I don't know how you define the random walk, but if you probably did the correct way, the meaning of this is the number of cigarettes the man had. So you're trying to say, okay, if I have this situation, how many smokes did we have? Did he have? So you're saying he smoked n from one box, and he smoked
And n minus R.
n minus r from the other one. So in total, he had 2n minus r. So you're saying m is equal to 2n minus r. I agree. Yes. Now you have to know how many should be here so that this situation happens.
Minus R. Initially, you would have 2n, because n in one box and n in the other.
Initially, you have to win. No, you can. In this situation, you can. The first match can be in this box. The first match you use.
No. The total number of matches can be 2n. Will be 2n because both of them have n.
I am a little lost.
A smoker has 2 boxes with n matches in the box.
Yeah.
Right. So initially, the total number of matches are 2n.
2n, yes.
Yes.
Totally agree.
So if initially we had 2n, and now we have 2n minus r. Does minus r make sense?
No, this is the number you smoked.
Yeah, it's like the number of steps you are allowed to have.
Yeah, I know. I'm just trying to make sense.
No, I get you.
I'm getting confused.
But it is difficult because there are things that are summing and things that are subtracting. Each time you smoke, you subtract one match. So if you initially have 2n matches, then you subtract 2n minus r, you have r matches. So this is just a consistency check. In this situation, at the end, you have your matches.
Okay.
So it is okay. So all of you have arrived at the conclusion that you could describe this situation as a random walk. Can you tell me how is a random walk?
The probability.
Yes, how is it described? So you have this dynamics in which you pick left or right, and you want to translate it into random walk.
So this probability that we have to write the same that it's for random walk, right?
The probability, yes, you want to translate it into terms of a
And
random
the
walk.
other,
So I want you to tell me, okay, how is the random walk you picked constructed in the end?
okay, so
Because what we are going to say is, you have this random walk in which in one step you do one thing, and we are interested at seeing the random walk at time 2n minus r. And we want to describe what has to happen at this time so that this event is fulfilled. And to see that,
That's what
for
I
me,
was
random
saying.
walks, you have to make drawings.
That's what I was saying. I couldn't visualize this one.
Okay, but tell me, how did you construct the random walk?
That's what I'm saying. I can't be.
with
I will take a match from the first.
So
No, but I agree, that's the way you did it also.
You go up when you take the match
from
from the
this
first
one
one.
and down from this one.
So the random walk is constructed by adding 1 in this situation or subtracting 1 in this situation.
Yes.
So
but why adding in that
It's just a direction.
in that box? Or it's a definition?
it's an arbitrary
Okay,
definition,
because
but
I was thinking that.
because you want to encode the situation at every time.
Okay.
And if you see, this is enough. Because you know, the time is essentially the total number of matches you used. And what is the meaning of this random walk? Okay, at time s, an arbitrary time, I will call it with another name, Sm, this will be the sum 1 to m of xi, that xi is the random variable like this, which essentially, if you pick from the right, it's plus, if you pick from the left, it's minus. So you can group these random variables, all the ones that have a one side and all the ones that have a minus on the other side. So this is the sum from 1 to m this is the indicator, like this is 0 if you did the opposite and 1 if you did this. Okay. I define it like this, right? Yes. So you sum over all the times you picked right, and you subtract over all the times you picked left. So essentially, this is the same as saying the size of the left box at time m n minus no, this was right box. You see it? It is all the matches that you picked from the left box minus all the matches that you picked from the right box.
This air, what is?
This I define like the matches that are left
Oh,
in
okay.
the red, in the right box,
So the total number.
and these are the matches that are left in the left
Yes.
box. So now that you have this interpretation, you want what to happen? You want this at time 2n minus r to be equal to what? Okay, you want to have picked all the matches in the right, all the matches in the left. So this you want to be n. And you want the matches left on the right to be r. And I think
Is there the, oh no.
you want the times. Okay, I will not write it.
No.
I'm sorry. So these are the times you picked right, and these are the times you picked left. You want to have picked n times left and n minus r times right. And if you do the subtraction, it is minus r.
That's what I was saying.
You were saying minus r?
Yes.
I didn't hear you, I'm sorry.
No, but okay.
Minus.
I'm totally confused now.
Minus.
Minus r.
Depends on how you define.
No, but how do you get minus r?
It doesn't small.
Hmm?
It depends on the direction.
Yeah.
If you choose different directions, I am just trying to be consistent with this.
No, that's okay, but I got minus r and I was like, how can we get a minus r?
But you get how you see how many times you want to pick the left and how many times you want to pick the right. And because one has a minus and one has a plus, so in the end, the probability we wanted to compute was a random walk at time 2n minus r is equal to minus r.
So now we can plug this into the formula.
Then you go to, yes,
Yes, which is n choose n plus, in this case n minus r.
this is like a binomial in which you have
Yes.
this number.
This
That is, but if you say, but that's what
You
I-
have this number of successes and this number of failures.
Yeah.
This n is the total number of matches that are in the two boxes.
No, this 2n is the total number.
N is the total number.
This is the amount you have to smoke to be able to be in this situation. Because in this situation, you emptied one box, which means you smoked n cigarettes, and in the other one, you smoked n minus
So
r.
we want to have one box empty.
One box empty and the other one with r matches left. And for that, you have to smoke 2n minus r cigarettes.
So and that one, and I don't understand very well that last two.
It's just factorized. This random variable, sometimes it's positive, which means you picked the right box, and
So
sometimes it's negative, which means you picked the left box.
But okay. So if you add it, you get n. Okay.
So after that, I changed the limit, so it should be.
Okay. Minus error.
the time in which you're seeing the random walk.
It's like half to path in the graph.
It is.
This is like half to path in the graph.
This is how to recognize the height that you want to achieve in the graph to be in this situation. You have to have had smoked n minus r cigarettes using the right matchbox, and you have to have had smoked n cigarettes using the left one because you want it empty. Which means that because every time you use the right one, it's a plus, and every time you use the left one, it's a minus, the random walk should be at this minus this, which is equal to minus r. So in this exercise, you have to construct the random walk to be able to translate it into random walk terms and compute the probability. In exercise 21, it's a little bit different because everything is already defined in terms of the random walk. In exercise 21, they just tell you that you want to compute the probability that a simple random walk is from time 0 to time to n, always on the non-negative side because it can't touch 0, and then at time to n it touches 0. They tell us that this is the probability. This is 2 times the probability of having the first return to 0 at time to n plus 2. And the hint is look at the paths. Which is like the yes. Obviously you have to do that, but my hint will be a little bit more specific. It will be look at the paths generated by the right-hand side and try to see in that drawing how you can recover these paths.
Nothing will, like, from the positive x-axis, everything has to be above it. It can't.
Yes.
It can't touch it. So every step is either.
It can't touch.
In this situation, it can't.
Yeah.
It starts from 0 and it only touches 0 at this time. In this situation, you can touch it many times. It doesn't matter. The only thing that can happen is that you go to the negative side and you have to be at 0 in this.
What is that? Do we have to find the function?
Yes, it's a finding in the theory, I'm sorry.
Yeah.
This is a probability that the first return to 0 is at 20, which means that you start from 0, you go apart, and you don't come back until 2n plus 2.
And this SK, it must be S10. Because I think that I don't understand if that part is it defined the first
The first one. Okay.
SN,
Yes.
but why is XK?
Now this means that for all these values of k, all the ones that go from 0 to 2n, not including them, this happens, which means that the random walk is always non-negative.
Okay.
So if you have to translate this into a drawing, we'll have that this event is something like this. You start in 0, you move around, but wait, you may touch 0 in the middle,
You cannot go.
but you cannot go negative. So this whole event means you can touch 0 in the middle, that doesn't matter. You don't have to go negative at time 2n, you for sure touch 0. But you may have other point in the middle.
So if we look at the paths in this case, do we construct paths with 0 and not n is equal to 0, but f0, f1, f2?
I mean, draw one generic
Just one.
way, like a representation, like in the way she was not understanding this event, I made one of these drawings and try to see how this drawing would be related to the other one.
Which other one? Do we have to make one for this and one
You
for
have two events. You have this one, which the graphical representation is this, and you have this one, whose graphical representation would be something like this, right? Would be you go up, and at 2n plus 2, you hit 0 again. The difference between both is that here you can hit 0 before, and in here you cannot.
Okay. And then what? That is really get stuck. Then I get stuck in then what? What do I have to do after that? Is there a formula?
You have to relate these two drawings.
The only thing that I can relate is 2n and 2n plus 2. The only thing in common is 2n.
Notice that it's very suggested that this is a little longer than this.
Yeah.
So you will have
That's
to
what I'm
cut.
saying, the only thing in common is two lengths.
Now, we first need to prove that S2n is equal to 0. Oh, it's not necessary.
S2n is equal to 0. That's a condition. You have to do something to this graph so that this condition is met, for sure. You got it?
Yes.
You want to explain it?
First, let me understand it.
Put it together, okay.
Put it together.
You want to go? Okay. I think, in fact, there is a mistake in the.
Yes.
Here, the random follow the binomial process according to the formula given by the professor. He said, in this case, we can consider K as the last position we have
The last position you have,
in the random.
the probability of touching
Yes,
in the last position, yes.
if I consider this position as my last position,
Yes.
in the right side. That means
Yes,
up,
yes.
not down, up. And the total number of states 2n. To be given by the combination of 2n position since the probability to go up or down is 1/2.
Okay. What you're saying here, this, if you normalize it, if you put a 1/2n, now this is a probability. And this probability is the probability of having one path
Yes.
that ends at the height k.
Yeah.
Right? Okay, that's just translating it. Okay. So this is equal to probability of S to n equal k. Okay.
Yes. And now we have to change this as 2n.
But notice that this is not the probability of this event.
This is not that.
I mean, if you put 0 here and 0 here, then this is the probability of the last condition. But you're not ensuring all this. You may, this event is this. You start at 0, you do whatever, and you end at 0. But for example, this path follows this condition because you end in the right place, but doesn't follow this condition, that you're always on the upper side.
And that means
So if you
That means that this is not the probability of the whole event. This is the probability of this event, which is larger. There are more possibilities to realize this condition than to realize this. Okay? The idea was more to see a drawing and relate this probability, which is very similar to this one. I mean, this is useful a lot of times, but when you're putting conditions of not crossing you have to use reflection principle or something more to, in the end, use this relation.
And we need to subtract something. Because we need to subtract what is in the mind.
That is formally correct. You're saying we need to subtract all the times, all the paths that do this, which is not correct, like go below. But that's very difficult.
You can also use the reflection principle, which will just say, which will cut the axis in which whatever events happen down there.
Or reflect it.
Yeah.
Okay.
So, again, I don't know how to do it.
But this is easier. You use reflection principle to get this probability.
So,
But assume you already know that.
so the thing is that over there we're multiplying it by 2 because there are 2 probabilities. What I understand is that the path is longer, but it's also because we're taking something and we're putting it, we're disregarding some values. So both of them are above the axis and not.
I will
have no
just,
idea what I'm saying.
I will make a drawing and you continue to think it because you're probably a lot of you are on the right track. If I get this path that has 2 extra values
Yes.
and I
But you also
mark
have to
1.
calculate,
There is 1 extra step here and 1 extra step here, which I think is where you were going.
Yes, but you're also multiplying it by 2.
I think this is incorrect.
Because that is what is bothering me right now.
Ah, okay. I think this is a 1/2.
Just the constant.
So, okay, the behavior is going to be the same, but you will have a different concept. And why 1/2? Because this event can be realized going up or going down.
Yeah.
So there are more possibilities on this side than this. Okay, we're out of time, but try to adjust this. The question, would it be useful for you to, perhaps 1 time a week, we select an exercise, you write it down, you hand it, and maybe I correct it or something like that?
Yes.
Completely optional, I will not make a list of who, so to be completely sure, don't hand exercises just for handing them, so you will have, it's just for you. I will not have a list where I say, this person gave everything and it was great, and this person, oh no, it's great. It's just so you have, perhaps, today participation was a little bit low, and when we go online, it's probably going to be very low. So for you to be able to replace this kind of coming into a Blackboard and sharing ideas and stuff. So the idea would be to not only, I mean, one exercise that is not very difficult, but the idea would be for you to write it as if you were explaining it, not just a pile of computations. Like here I use total probability to unconditioned. Here I compare this path and a drawing with this other path because it's reasonable for something like that. Okay, then I will think one of these exercises and I will write on Slack, and you can work it out and then I correct it.
What do you think more about this?
Look at the drawing and then put the idea together.
I think from the drawing I get it. I just don't know how to say it. That is my question. Right.
I think the idea of the exercise was more to see the drawing and
But we don't have to subtract nothing. Because I think that we have to subtract that is above the axis with the.
you have to subtract.
Not subtract, reflect.
It is like you're
So-
moving the axis
Yes.
and
You're-
shortening the time at
Yes.
the same. But for every one of these paths, you have one of these. No, okay, you have a.
No, it's.
It is okay. It is a 2
Yeah.
because the normalization also changes.
I-
Okay, now I get why.
That's what I was saying, that it's double the.
So then you have a 4 because the normalization has a 1/2 to the 2. So it was correct.
My brain hurts. Oh, yeah.
Sí, sí, después arreglamos.